what's that? Transverse. What's that mean to be transverse?
Horizontally.
All waves are horizontally. What? Don't use the word it. Nope. Close. Good. The particles in this wave, so right there, move perpendicular to the energy it's transferring. Remember that because this T is an upside down perpendicular sign. That's a transverse wave. What's the other kind of wave? Longitudinal. How is that different?
Back and forth, up and down.
Particles move parallel to the motion of the wave. Longitudinal has two L's in it, as does the symbol for parallel. Those are our two kinds of waves. All the properties, as we see up there, are the same in both kinds of waves, but the transverse ones are easier to draw. We pretty much only talk about transverse waves, but all the rules and bouncing and all the stuff we'll discuss today are exactly the same for both kinds of waves. But longitudinal is just tough to deal with. Drawing. So, be ready for that. Okay? Question? Good. There's the one question. So, let's make some meaning. Today we're going to discuss something called a standing wave. And what a standing wave is a wave that appears to be standing still, even though really is vibrating. It's typically set up and you have a wave that's constantly emanating out of the source. Most waves are standing waves, basically. Light waves from the sun aren't just single pulses, like we said yesterday. They're a constant flow of energy out of the sun. And so you would see that as a standing kind of wave. They happen in other cases, though, because you have a wave confined in a space, and so it bounces off one end and kind of reflects on itself. And when that happens, certain mathematical operations take place, so to speak. Now, first, let's talk about waves reflecting. You should have seen some of this yesterday, a little bit there. Here is here's a wave. Like that. There are three possibilities for this side of the wave. You can either have fixed end, which is this string/spring being clamped down, a loose end, where it's tied to a ring that can move up and down freely, or no end, or it just goes off to somewhere else. So we're going to investigate what each of these different sorts of ends does. So in this case, if I were to send a pulse down the string with no end, would the wave reflect back? Let's find out. All right, here we go. Good. So it didn't reflect back. That's pretty obvious. You do the same thing going down. A whole bunch. And they all go out there. Ooh, no end. Ooh. Questions? Your response. Loose end. Now, this is going to reflect back to you. A little bit. How about why only a little bit? We're going to assume for a moment that's going to reflect back. Do we think it will reflect back? So if I send the pulse down on the top of the wave, like this, when it reflects back, is it going to reflect back on the same side of equilibrium, or will it be inverted? Why? So this is going to go up and come back down, and the wave is going to somehow invert. Good. So when you have a loose end, the ring just moves up and down, or down and up, and it bounces the wave back the exact same way that it came in. What's that? Yeah, we have to do that observer. So a loose end, if there was the test question, how does a wave reflect back? If there were a loose end, how would we answer that? Anybody? Same way it went. It does not invert as the key over. So if it was on top going into the loose end, it's going to go back on top. If it's on bottom into the loose end, it's going to go back on the bottom. Okay? Question? Make sense? Okay, now if we have a fixed end, what's going to happen? Why? So we all should know, if we watched a second ago or watched our lab yesterday, we should know the wave can invert on the pulse and the fixed. Let's double check. Invert, yeah. Why does it invert? Why would it invert? We all know that it does. No, there's no argument. Why does it invert?
Because it doesn't want to move, so it cancel out the waves maximum for 1 or something.
Put the law on here. No. That explains why it bounces back with the same amplitude, but not why it inverts per se. Why? So the other one, when it came, the other one came down.
Wait,
Really?
is it every atom?
Which is Newton's third law. Very good. So this wave comes in before, in the loose end, it pushes the spring up, and gravity pulls the spring back down. Agreed? With the fixed end, now this tries to push up on that clamp, but it can't. So if you apply a force up on the clamp, what's the clamp do? Pushes back down, hence causing the inverted wave to go back. The clamp is, this is like a table thing, or I don't know, it's clamped to something. So that's why that inverts on the same side. We have the friction at 0 right now, so that's why it doesn't slow down. If we had some friction in here, it would slow down over time right there. That doesn't know that. The friction comes from the fact that in our lab, it's on the ground. There's some friction. Just when you have a spring and it coils and uncoils, just that metal moving. Like if you ever take, you take a piece of metal and try and break it, you bend it in half a time, so it crease, it gets warm in the center. When you bend and stretch metal, it gets hot. So that the friction, the internal molecules of the spring do things with friction. Pretty exciting stuff. So that is pulses reflecting. Questions about that? So loose end, no inversion, fixed end is inversion. And we all know how to turn one. I'm going to ask you again tomorrow. I don't want any blank stares.